It doesn't matter if it's here or there, it's a truck. We as humans fundamentally deeply understand three-dimensional reality. You understand the symmetry of camera perspective. If I get a little closer, you don't even take for granted that all of my pixels are a little bit bigger now. Or if I go a little farther back, or if I rotate a little, like you are completely factoring that out constantly. We've trained computers to factor out translational symmetry and scale invariance. Rotations are still quite challenging. Okay, there's still a lot of symmetries. It's very hard to train machine learning algorithms to respect and understand symmetries in your data. That's one of the open problems. Okay, convolutional neural networks are good for images. Recurrent neural networks are good for audio and temporal. I realize now that this is a slide that I use when I have my light board and I can actually draw. This is when you can connect back. I forgot my arrow, so this is a really lame recurrent neural network, but if you can connect back to previous levels and feed information back, you can create these memory loops. Okay, and that's really good for things like speech processing, dynamical systems modeling. So you have these LSTM, long short-term memory networks for feeding back information. The ResNet, these deep residual networks, have jump connections that allow you to carry information over longer periods. One of my favorite networks for fluids for this community are autoencoders, because it fits in so naturally to what we already do on a daily basis with POD and DMD. Okay, so I'm taking for granted that basically all of us already do POD and DMD and feel very comfortable with taking high dimensional data, recognizing that there are patterns in that data, and then extracting kind of a low dimensional representation. In the 80s, it was shown that the principal component analysis, or the POD, could be written as a simple linear neural network. Okay, if I have a big neural network with a big input dimension and a big output dimension, and this is my image of a flow field, and I'm trying to reconstruct that image of a flow field, but I'm choking it down to maybe 3 nodes in the middle, that's a 3-state, that will pull out your 3 most significant POD modes. Okay, and what's nice about this is that you can relax those conditions. Now you can allow your network to have nonlinear activation functions and a deep architecture. And so instead of pulling out a linear POD subspace, you can pull out a nonlinear manifold that your data lives on. Okay, so remember in the fluid flow past a cylinder example, your flow lives on this parabolic manifold. POD would pull out the 3 coordinates that manifold lives in. This deep autoencoder would pull out the 2-dimensional parameterization of the manifold itself. Okay, and this has been used in fluids since 2002. I'll talk more about this. Milano and Koumoutsakis, I think, were the first to use this deep autoencoder architecture for fluids, but now it's becoming pretty pervasive. It's a generalization of POD. Okay. So I like to give a caution. Maybe I've already given enough caution. Neural networks are very prone to overfitting, especially when we build neural networks based on our puny data sets. Google has massive data sets and massive resources to prevent overfitting, but we have to worry about that. Generalization is a big problem. Neural networks are, if you take one thing away from what I'm telling you about neural networks, they are really good for approximating nasty functions and interpolating between data you've already seen. They are the best interpolatory algorithms out there today. They're no good for extrapolation. If I train my data on my network on data collected here, it will not be valid out here. Because whatever the shape of the function is here, the network does not make any assumptions that would generalize out here. Okay? As physicists, we care about generalizable models. F equals ma is a great example. Okay? It's a big problem with neural networks, a huge problem. Interpretable and explainable. If your neural network has 10 billion parameters, how are you going to interpret it? How are you going to make sense of what decisions it's telling you? Okay? And incorporating physics is one of the really, really active areas of research. So in the US alone, I was writing down some numbers. I think in the last 2 or 3 years, there's probably been about $200 million of grant funding just on incorporating physics into machine learning. I know that there's similar efforts in Europe for this. It's a very, very challenging. So I think that this is the second wave of machine learning. The first wave were these kind of low-hanging fruit image classification static dataset problems. The next wave is going to be physics problems and engineering principles. Okay, and it's not exactly a caution. It's also kind of an opportunity, right? There's a lot to be done still. It's not a solved field. Okay, cross-validation. Remember yesterday we had our accuracy versus model complexity? I just want to point out you have to cross-validate your models. You cannot train a model on training data and believe anything you get. Does everyone know that in your heart? Does anyone have any doubts that you shouldn't be cross-validating? If I shake you awake at 2 in the morning, you should know how to cross-validate your models, okay? Hold out some of your data for testing. And in the next lecture, I'm going to give you some examples of where cross-validation is not as easy as it sounds. So in the ImageNet example, cross-validation makes sense. You just hold back, 10% of your images and you use those to test if your algorithm was any good. That's fundamentally relying on the idea that your task is an interpolation task. That in those, 10 million images, I've seen basically everything I care about. It's not good for extrapolation. So I'm going to give you some examples in the next lecture about training and testing and cross-validating on interpolation problems versus extrapolation problems. Okay, there's a difference, and it's a subtle difference. So you've already seen this. You have to cross-validate because then your models might well be overfit. Okay, good. Okay, good. Does anyone have any questions? I've just got a few more vignettes I'll go through. Yeah? What do you mean by overfit? Overfit, yeah, sorry. Good. What do I mean by overfit? By overfit, I mean, so there's this great quote that, with 3 parameters, I can make an elephant. With 4 parameters, I can make it dance. I forget who said that. Anyone know?
There was Gauss who said with 7 parameters I can make an elephant walk on the rope, and with 11 parameters I can make him dance on the rope.
Yeah. So the idea is with these highly expressive functions, a deep neural network might have millions or billions of free parameters that you get to tune. We know that we can over parameterize our model to fit. So for example, if I gave you, I'm going to do an example right now. I'm going to give you data points. My finger is going to be the data points, and you're going to tell me what function I'm approximating. Okay, I'm going to give you data, 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 data. So I've heard parabola, sine, those are logical. Okay, maybe a cubic. But there might have been some noise. I might have, had some beers. So if you allow your machine learning model to fit that with a polynomial, and you're just trying to minimize error, it will use a 10th order polynomial, and it will go through exactly every single one of those points. And it'll be a garbage model unless you had some extra points that you held out to validate. Okay, that's what I mean by overfitting. Okay, good. Neural networks are very commonly used now in dynamical systems. This is one of the areas of active research in incorporating physics. I think Bernd's going to talk about machine learning for reduced order modeling, which is definitely in this vein. I'm going to talk about this for fluids later, but I'll just give you kind of an idea of what I mean here. So you can also build a network that, given some state vector x, will predict x dot. You can train a network to do that. So you can build some representation of your dynamics f. Again, it will only be valid as an interpolation where you've already seen data. You can then use that to iterate using something like a forward Euler or a Runge-Kutta scheme. This is pretty common. You can also learn the time step flow map itself. You can learn an integrator. This is super cool. One of my former PhD students with Nathan Kutz, Sam Rudy, learned how to incorporate Runge-Kutta time stepping into this. That was pretty neat. On the training data, it does really well. You can, this is for the Lorentz system. You can integrate this forward and you get these trajectories. Some test trajectories, though, fail, and they go to these limit cycles or fixed points. So you have to be pretty careful about training with a richness of data so that you've seen everything that you will see in the future. Okay, so On a tractor, sometimes it works, but sometimes it doesn't work that well in testing. There's a pretty nice kind of zoo of machine learning algorithms for modeling dynamical systems. These long short-term memory algorithms, these recurrent neural networks that have been used for a long time in recognizing speech. So like your Google Translator is using something like an LSTM or an RNN. You can use those for modeling dynamical systems. So Pantelis at ETH built a nice network to do that. These reservoir computing networks are pretty cool. These are like really shallow networks where you basically have just this big reservoir of nonlinear functions and you get to train how to connect them up. That's been pretty interesting. And then also people are doing a lot with autoencoders and building models of the dynamics in these latent variables. That's just a couple of examples. This is that paper using reservoir computing. I think this is pretty cool. So they're running this on, I believe, the Kuramoto-Sivashinsky equation, which is a chaotic spatial PDE. So this is space, and this is evolving in time, and it has these kind of chaotic fingering. And this is the true high-fidelity numerical model. This is their reservoir model. So it gets the right qualitative behavior, and it agrees quantitatively for some period. And so this error takes a long time to grow. That's pretty cool. If you change the color bars a little bit, you can actually see it already has error early on. So you got to be careful about how you color your plots. But it's a pretty impressive algorithm. Okay, good. Does anyone have any questions at this point? Yeah, in the back.
Okay. I have a very basic question about like back to the beginning of the lecture about definitions and where does the term deep learning fit into the classification? It's just related to deep neural networks or can be extended to other methods or algorithm?
Yeah. So deep learning refers to machine learning using neural networks that have many, many hidden layers that are deep in the number of layers that they have. And that's a modern trend that has been enabled by advanced GPUs, better training algorithms, and enough data to fit those many millions of parameters. But it's a deep neural network, many-layered neural network. And everyone's having competitions to see who has the deepest neural network, and it's a moving target. Yep. Good question. Any other questions?
As a follow-up to his question, how would you classify deep neural networks as supervised, unsupervised, semi-supervised, or they're applicable to all class of problems?
Yeah, so this is something that we have heated debates about sometimes. It's a little hard to pigeonhole it too much. A lot of deep learning applications are supervised learning applications. Image classification is a supervised learning application. A lot of deep learning applications are semi-supervised. So these deep generative networks are semi-supervised. Google DeepMind is deep reinforcement learning. So that's, again, semi-supervised. The deep autoencoder, the one that does the nonlinear principal components, that's not exactly supervised. You're using the data itself as the label. So it's hard to even know what that is. I would call that an unsupervised learning. So it's a little hard to say. Any other, yeah.
Have you heard of neural ODEs?
Neural ODEs, yeah.
Have you compared how they would work against your Cindy model?
Yeah, I mean, so people are definitely making those comparisons. I think neural ODEs is really exciting. It's interesting if you So there's no method that's going to be kind of a panacea or a silver bullet for all problems. So there are some problems where you're going to want the arbitrary function approximation of a neural network because the vector field is that messy. There's other problems where you're not going to want that. You're going to want it to be faster. If you want to do model predictive control, you're going to trade some of that accuracy for computational flexibility and efficiency. But there is an interesting point. Some of these kind of deep residual networks that are now being shown to be quite good for ODE simulations. Oftentimes, if you take a task that you think is going to be trivial and you try to train a neural network, 6 months later, you realize that it's not as trivial as you thought. Okay, that's been every paper we've written on neural networks. There was 6 months where we could not figure out why the thing that was obviously should work didn't work at all. Okay, and we tried this. We tried to build a neural network that would essentially learn the identity map. We were trying to build a deep autoencoder to learn the Fourier transform to solve the heat equation. Okay, that would be like we were trying to learn the Fourier transform, and then we were trying to learn the Cole-Hopf transform to transform Berger's equation into heat equation. And at some point we realized that there was, a part of that where we needed an identity or something similar to the identity, and it was actually really, really nasty to build out of these ReLU units. And the residual network is nice because all of these jump connections are basically carrying the identity with you. And if you think about your favorite ODE integrator, like think about, I don't know, RK4 or on Euler. It's built on, actually, I just had this up, right? Your integrator is basically an identity plus an epsilon times your vector field. So that's why these residual networks are so good, because they're carrying the state forward and you don't have to like build a network to learn how to carry the state forward. So I think that's why they just have the same structure as integrators. So that's very, very natural. Okay, good. I'm going to talk about two more things and then we're going to have coffee. Okay, so there is a debate in machine learning, especially for physics, about whether or not you want end-to-end solutions or whether or not you want to focus your machine learning on very specific subtasks and then piece them together like an engineer would as a machine. Okay. And so I'm going to tell you about work in what we call discrepancy modeling. And this is work with Nathan Kutz and also Cardi here. You can ask him. It's this idea that instead of trying to learn everything from scratch with a neural network or whatever machine learning algorithm you like, we often have a lot of partial knowledge about the system. So for example, when I'm building a controller for a robot, I know that that robot has joints. And I know that there's basic conservation laws and symmetries and things like that. That is extremely hard for machine learning to learn symmetries and constraints. It's very hard to teach an algorithm that energy is conserved. Okay, I haven't seen it happen. But if you know that, you can bake that in and save it a lot of trouble. Okay. Similarly, there are things that are hard for us to model physically, like wind resistance and nonlinear friction. Those are perfect for these arbitrary function approximators. Okay, so you start with this imperfect model of the world. Instead of trying to model everything from data, just try to model the discrepancy between your observations and your model. Okay, so here's a nice example. This is the one I used to demonstrate this. This is Cardi's work, and he's here, so you can ask him about this. But we had a pretty good model for our double pendulum experiment, right? This is textbook Euler-Lagrange. But we measured this thing as accurately as we could, but we have some uncertainty in our measurements. There's nonlinear friction and bearing chatter. It's not perfectly described by that Euler-Lagrange model. And when you use that idealized model for a control law, it doesn't quite work for the swing-up stabilization. Whereas if you can learn some of the discrepancy between your observed data and your ideal model, you get kind of the best of both worlds, and you get to focus your learning only on the part that you don't already have. Okay, so we think this is nice for physical modeling. You can also use this for like digital twins and robotics for high precision manufacturing. So this is work we're doing with Boeing that I think is pretty neat.